The third question, even more algebraic. If you look at this particular question number, question 7, it was actually the last question on the paper of this exam paper. I have had to change it slightly though, which would probably have made that 2 marks, so possibly not as tricky as it was. So the first part looks really quite intimidating, but actually it's just a slightly more generalised case of what we did in the previous question. So in this question here, we were given the value of the radius. In this question here, we're not given the value of the radius, we're told that that's equal to a. So it just means that there's one more unknown in there. Of course, we know what g is, so there's 1, 2, 3 unknowns. In question 2, there were just 2 unknowns, so it's just that we've got that additional algebraic term, the radius, in there. Other than that, the maths stages, the processes that we go through is exactly the same. We have got this time, however, something happening on the outside of a sphere. So it's balanced on the top, it's then disturbed from rest, so of course it starts hugging the outside of the sphere, but at some point it will just kind of, fall off, come off at a tangent. And essentially the question is building up to that. So you could, I suppose, be faced with this question, given this situation, no part 1, part 2, find the value of theta when the particle falls off the outside of the sphere, so you would have to go through these same stages. Well, we're going to start, of course, with the first bit. I think, this is slightly different to the previous ones we've done in that we're starting at the top, so you just need to think a little bit more about where to set your 0 level at A. So I suppose we could keep 0 at the bottom, 0 there, 0 at the top. You might think, because we're starting at the top, call that 0, but then of course as we go round we're going to be going negative distances, and I would always try and avoid negative if you can. If you start there, okay, A is easy, but it makes B a bit more complicated considering that height, so make 0 make the centre of the circle the 0 level, and it just means that things keep a little bit simpler as we work through. Of course, V is equal to 0, it's disturbed from rest. So the gravitational potential energy plus my kinetic energy is equal to mGa plus a half m times by v squared, which is 0. So we just have mGa. So for B, so B's here. Now, because I'm taking that as my 0 level, all I actually need to look at is that length there, which of course is equivalent to this length here. So that's the length I need. Because I've got an angle of theta there, I've got a right angle there, that again is the cosine component. It's the adjacent side. This length, well, we don't know what it is. It's we've been told to take it A. So we are going to have our height A cosine component, so A cos theta. The velocity, don't know the velocity. So gravitational potential energy plus kinetic energy, mg times by A cos theta plus a half mv squared. Now, the expression that we need to find is in terms of omega, but kinetic energy is most definitely a half mv squared. What, of course, we can do now or at a later stage is use our equation V is equal to omega r to change that into omega. But I'll stick with this for the moment when I do my conservation of energy, equating these two expressions. So mGa, total energy of A, or at A, is equal to the total energy at B, mGa cos theta plus a half mv squared. And look, the m's all cancel. I have got Ag, and I think I'll multiply by the 2 as well. So 2AG is equal to 2GA cos theta plus V squared. And this is where I will use my V is equal to omega R. V squared then will be equal to R is A, so A squared omega squared. So I'm going to sub that in there. So that gives me that 2GA is equal to 2GA cos theta plus V squared, which is A squared omega squared. Every term has got an A in. Cancel, cancel, one of those will cancel. I need to make A omega the subject. So A omega, sorry, of course it's omega squared. I've got the 2G there, and I will need to subtract that expression. And then the only thing that happens next is we just need to do a bit of factorising. So that pops out quite nicely. And of course, if you had taken anywhere else for your zero level, you'd have still have got there. It just that you might have had a few additional terms, particularly if you took the bottom of the sphere to be your zero level. But just think, you know, which makes most things positive, or more positive, and certainly having just that little green distance to work, leaving with an A cos theta, was the simpler thing to do. Okay, so to work out, and I'm just going to highlight that because I think we need it in the next part. So the next bit, find an expression for R. So I need to look at what's going on at this point here. So let's just draw that bit out again. So here is my particle, what I've called at B. It has got the weight acting down. So consider that as being the centre. The normal reaction, of course, acts in that perpendicular direction. So that is going to be the same line as that line to the centre. So that is my normal reaction force. No other forces happening there. R, of course, is going, well, it's not in the direction, but it's along that direction, but it's opposing, it's against the acceleration. It's the weight component that is actually contributing in that direction. So if we consider this right angle triangle there, again, if you want to draw it out, that's mg. This is my direction there. That is my right angle. It's that component there. If I draw it on the diagram, it would be this component here. There's my right angle. I need an angle. Of course, that is theta. I have got an alternate angle there. Not really much space to draw it, but that is my theta there. I can draw it on that diagram. It's the cosine component. So that green bit there is acting towards the centre. That's going to be mg cos theta, and then r is opposing the motion. So, of course, I've considered the energies. Now what I'm doing is resolving using F equals ma. I get that mg, as I said, it's the cosine component. The r is going in the other direction, and that is equal to ma. And this time I'm going to use omega squared r. And r is A. I want an expression for r, so before I do anything else, let's just make r the subject. So it'll be mg cos theta minus m omega squared A. And of course, this here is what we had in the previous part of the equation, the bit that I have highlighted there, and actually it's this bit here, isn't it, in the question. So I'm going to be putting that right hand side in place of there. So r is equal to mg cos theta minus m multiplied by 2g 1 minus cos theta. And then it's just a matter of expanding that. 2 mg multiplied by 1, and then 2 mg multiplied by cos theta, but it's two negatives, so plus 2 mg cos theta. I've got 1 and I've got 2, so I'll have 3 mg cos thetas minus 2 mg, and then shall we just factorise? 3 cos theta minus 2. So there is my expression. So all of this we've done without any numbers, so we haven't been given any values at all, so this is all just general case. Right, so final part, and as I said, it is now a much shorter and much simpler thing, because it's talking about when P loses contact with the surface of the sphere. This, of course, occurs when R is equal to 0. The thing that's keeping that attached to the sphere is that normal reaction. So when that's 0, it will lose contact. So I just need to consider 0 in that equation above. 3 cos theta minus 2. It, of course, has mass. G is 9.8, so that cannot be 0. So it means that we, of course, we need to consider the trigonometric thing, because we need to work out an angle. So we need to solve that. Cos theta is 2/3. Theta is equal to inverse cos 2/3, and that is 48.2 degrees. Okay, so even though it's algebraic, actually what happened, it was kind of very formulaic, just the same as what we've been doing in the previous two questions.